And we're going to specifically look at some of the math and the formulas. Again, looking at the exams, there were people, first of all, one thing that I discovered last night was there was a typo because I was going through working the problems, and there was a typo on the quiz. And several of you understood what it should have been, and you automatically corrected it. There was a number, I think it was 2.4 times 10, and it should have been 10 to the 14th. It was on the exam as 2.4 times 10 to the 14th. My formatting of the superscript didn't hold when I copied it from Word into PowerPoint. That happens sometimes. I go back and try to catch them all. So what many of you did was said, well, 2.4 times, actually it was 4, I think. Anyway, the numbers, you went through and you did the math, and you came up with, in this case, it would be like 2,000 and some odd hertz. What I was meant to communicate was 2 times 10 to the 14th hertz with an exponent. So you did the math, you multiplied it out, and then you tried to apply it to the formula. Generally speaking, when we're looking at frequencies, they're going to be large numbers, okay? So you should anticipate, I would hope that some people would have said, is that a typo? Because every time we've worked these kind of problems, it's been a huge number rather than a number in the hundreds or thousands. Or a couple questions like, for example, on the homework that have nanometers written out. What is a nanometer? Well, it said right on the top of the page, nano means times 10 to the negative 9th. Okay, so make sure when you do those kind of word problems and they say nanometer that you don't use 712 as if it's meters. It's nanometers. You've got to put it into meters. So you've got to use a full times 10 to the negative 9th. Let's go back in our books and work through the example problems. And again, these are fully laid out for you in the text, but it was pretty clear from the work that was shown on the quizzes that there's a lack of either understanding or a lack of ability to just work the formulas. And just many of these are just plug in the numbers and do the math. Happened at our home last night. I would encourage you again, whatever calculator you're going to use, and I understand if you borrow from the math department, aka Mr. Kyle, if you borrow from math, that you're kind of restricted because you don't necessarily take those calculators home and use them, but whatever you're going to use on the exam, use that same calculator when you work the problems. In my home, somebody was trying to use their phone calculator. When on the exam, they won't have their phone. Then I just had to quickly say, what are you doing? You're not, every calculator, especially scientific calculators, use, and primarily scientific notation, slightly differently. And you need to be incredibly comfortable with the calculator you're going to use in the exam. Working the exam when you're struggling with, did I get the formula right or not, is not the time to say, am I getting the right answer because I pushed in the numbers wrong? I did the monkey skills wrong entering the numbers. Be confident that you can do that. If anything, go through one of the problems from the book, an example, and put the math in your calculator and see if you get the answers that they give you in the book. Okay, and just walk through it with your calculator. Example 3.2 starts with talking about this violet light wave. It says the violet light wave has a wavelength of 405 nanometers. So a wavelength of 405 nanometers. That's going to be the same as saying 405 times 10 to the negative 9th meters. Okay? 405 nanometers is the same as 405 times 10 to the negative 9th meters. What is its frequency? What is its frequency? So, we're going to have that distracting noise because, frankly, it is really warm in here. I don't know how you guys are wearing sweaters, but it's really warm in here. As a matter of fact, I had the doors closed. One of the teachers came in and said, "Oh, this room is nice and hot like a sauna. My room feels like it's air conditioning. You want to switch?" I said, "Please." "Oh, but we need the lab space. Sorry, can't. This is one of those few classes that can't just swap rooms." So, we have wavelength. We're asked for frequency. Yes.
Is it always -9?
If it's nano, it's 405 nanometers. And on the problem, like on the top here, it says, it always gives us what is C, the value of C, And what is the prefix nano mean? Here, times 10 to the negative ninth. Because remember, they told you you didn't have to memorize nano. Now, I would disagree. I think nano is something you should memorize. But since they said you don't have to, they include it with every problem. What other piece of information did they include that I just mentioned here? They gave us that C equals 3.0 times 10 to the 8th meters per second. Okay? As I mentioned before, in real science, you don't always know what variables you need, so you go out and you sample lots of variables. There's a lot of information that's out there when you actually do an experiment that you end up not really needing. It's kind of simulated here when they tell you, oh, by the way, C equals 3.0 times 10 to the 8th. Guess what? You probably need to know, for however you work it out, that C equals 3.0 times 10 to the 8th, because they don't have room to list every single variable that's out there that you don't need. So I can tell you what you do need, most of the time. So we're trying to figure out frequency. What we need is some way to relate these three things together, because if we can relate it using a formula that includes these three variables and only includes one variable that's not solved for, we can rearrange the formula to solve for that unknown variable. In this case, the unknown variable is frequency. We only have two formulas for this whole module, right? Two formulas. One of them, the way I write it, is that C equals lambda f. And the second formula is the energy equals hf. Now I hope, again, only because it's come up in tutoring and in working with people, that when you see this, that you recognize that this means that C equals lambda times f. You're going to multiply those two things together. And in this case, that energy equals h times f. We know what C is, that's our speed of light. We know what lambda is, this upside down y with kind of the curvy tail. That is wavelength. The F's stand for frequency, E stands for energy, and H is Planck's constant, right? You will be given this and this whenever you need it. So generally, if you're given one of them, and then as a constant, because these things never change, they're always the same, and if you're given one of the other unknowns, you can always solve for the final unknown. If you know one of the variables, you can solve for the unknown variable. In this case, the formula we're going to be using is the speed of light, or the light formula, that C equals lambda f. Now, one of the things you have to be able to do is to rearrange this formula so that your unknown variable is all by itself on one side of the equal sign. This is very basic algebra. It's like algebra 1 stuff, okay? Early algebra 1 stuff. What is our unknown variable? What are we trying to solve for? Okay, we're trying to solve for frequency. So we want frequency to be all by itself on one side of the equal sign. We're going to get frequency all by itself on one side of the equal sign by doing an opposite operation. In this case, we have lambda times f. So to get f all by itself, what do we need to do? If the operation is multiplication, we need to do the opposite, or divide. Divide both sides by lambda. In the resulting formula here, lambda cancels lambda, and we're left with f equals c over lambda. We have c, we have lambda, we're looking for frequency, f. You just plug in the numbers. So I recognize too from the quiz that some of you are struggling with what I believe is you don't understand scientific notation. And unfortunately, where we are in junior year in science, scientific notation is something that you really need to have a handle on by now. And I appreciate that if you are struggling, and maybe we can cover that in tutoring, but to go detail into that now is kind of away from chemistry and into math. Actually, scientific notation is something that I've recommended that we have as part of a summer school before chemistry, so that when you come back in, you're refreshed on the math part that you need to know. Where we are now, we have to deal with where we are. Okay, so if you need help on scientific notation, talk to myself, talk to Mr. Kyle, get some additional help on that. You got to take ownership of getting help if you need it. So frequency is speed of light divided by the wavelength, because frequency and wavelength are inversely proportional to one another, right? What does that mean? It means that when one goes up, the other one has to go down. In this case, the product of the two is always equal to the same thing. So if one doubles, the other one has to be cut in half. If one triples, the other needs to be cut into a third, because the product has to be the same. Because for our purposes, the speed of light does not change. Okay. We're leaving that authority to God. We're just going to manipulate the things that He's allowed us to manipulate. So the frequency is equal to the speed of light divided by the wavelength. We just plug in the numbers. Here it's 3.0 times 10 to the 8th divided by 405 times 10 to the negative 9th. Now you could have written that 4.05 times 10 to the negative 11th. Okay, but we'll just leave it like that. Or excuse me, to the negative 7th. You would have gone up 2, so it would have been negative 7. Matter of fact, in the example, I see here that they did that. So let me go ahead and do that just for consistency with numbers in case you're comparing your notes to the book, and I haven't decided whether the exam will include notes or not. Part of that is I want to encourage you to take notes because the quiz did allow you to use your notes. So I'm hoping that you look towards that, you know. So if don't depend upon the notes, but if I let you use the notes, that's a motivation to take good notes. Not because the test is necessarily that hard, but because I want to motivate you to take notes and to actually learn the material. You will learn the material better if you take notes, even if you think you don't have to. It's just scientifically proven you will. All right, so 405 times 10 to the negative 9th. If I make this one smaller by moving the decimal over 2, I need to make this larger by 2. And to make it larger from negative 9 by 2 is to move it more positive, so it becomes negative 7. Again, that's scientific notation. Hopefully, both would have worked. 405 times 10 to the negative 9th or 4.05 times 10 to the negative 7, they're the same number. There are two ways to write the same thing. Then from here, we just go through and do the math. Now let's first of all, before we put it into our calculators, because let's say my calculator broke at the last minute, I'm using somebody else's calculator. I don't know if I know how to use it right or not, but I'm going to do my best. But let me see if I have a ballpark answer that's right. What's the ballpark answer? What I'm going to do first of all is look at the coefficients. Here it's 3.0 divided by 4.05. Let's estimate that. Do you see that that's basically 3 divided by 4? Okay, so let me go ahead and do the coefficient work first. 3 divided by 4, and I'm going to do this, put the squiggly line. That means approximately equal to. I'm not saying it's equal to. I'm saying it's approximately equal to. 3.0 divided by 4.05 is about 3 to 4. It's about 0.75. Are we good with that? Pardon? No, you said something. I didn't want to ignore your comment if you... Okay. Okay. So 0.75. We're good with that coefficient part. Now let's look at the scientific notation portion. Because 3.0 times 10 to the 8th is the same as 3.0 times 1 times 10 to the 8th. And 4.05 times 10 to the negative 7th is the same as 4.05 times 1 times 10 to the negative 7th. We can justify doing this mathematically. But we've got 0.75. Now let's do the other portion. Whenever we divide by scientific notation, okay, we're dividing times 10 to the 8th divided by times 10 to the 7th. What operation do we do on the exponents? We subtract. Good. Division by the scientific notation, by the exponents, is a process of subtraction. So what this becomes is times 10 to the first exponent is 8, and we're going to subtract the denominator's exponent. The denominator's exponent is negative 7. When you subtract the negative, it's the same as what operation? Adding a positive. So we're going to subtract the negative. So we're going to subtract the negative 7, which is adding a positive 7. Subtracting the negative is the same as adding a positive. So 0.75 times 10 to the 8 plus 7 is 0.75 times 10 to the 15th, which is equal to 7.5 times 10 to the, so I'm making this one bigger, I need to make that smaller, it would be about the 14th. Yes? How would this be negative 7? Because over here is 405 times 10 to the negative 9th. Because I moved the decimal over 2 places to make it 4.05 instead of 405. So when I took it from 405 times 10 to the negative 9th, I rewrote that as 4.05 times 10 to the negative 7th. It's the same number, just moved the decimal and showed it slightly differently. That allowed me to see 3 over 4 instead of 3 over 400. And I counted for that in the exponent. So this gives me approximately 7.5 times 10 to the 14th, approximately equal to. When you actually put it in your calculator and punch it out, the book tells us that we should come up with an answer of 7.4 times 10 to the 14th. The question is, 7.4 times 10 to the 14th what? What are the units on this? Well, we're looking for frequency, and we know that the units of frequency are hertz. It's a hertz, right? What is another name for a hertz? Mathematically, when we derive the units, a hertz is a 1 per second. A 1 per second. So we could also write this as 7.4 times 10 to the 14th, 1 over seconds. That's the units of 1 over second. How do we get 1 over second? Well, let's just look at this formula and only look at the units. The frequency is equal to, what are the units of the speed of light? It's in meters per second. I'm going to write out sec just so we keep it straight. Normally I just put an S, but meters per second. And the wavelength is in units of meters. Meters. That's why we can't use nanometers. We have to convert it into meters, which is why we have to put the times 10 to the negative 9th meters whenever we see nanometers. Okay? So my units of frequency are meters per second per meter. To do the math here, hopefully you see that meters cancels meters. If you don't see that, you can always put it all over 1. And now we'll do the math. 2 fractions. To divide by a fraction, just like we said, to subtract a negative is the same as adding a positive. In mathematics, when you divide 2 fractions, dividing 2 fractions is the same as multiplying by the reciprocal. So this becomes meters per second times the reciprocal of this, which is 1 over meters, and meters cancels meters to give us 1 over seconds. Okay? So that's how we come to the derived unit. Remember, a derived unit is, it doesn't, it's not like something that makes obvious sense to us. An obvious sense to us is meters. A derived unit is a 1 per meter. Not as obvious. So we call that a hertz because we have the concept of cycles as being how many per second and call it a hertz. So I encourage you to either stand up or take your sweater off, okay? So parts to this, write down the variables, figure out the formula you need, put the formula in the correct form so that you're solving for the unknown variable, plug in the numbers, do the math. It's cute, got pinky rings or something too. And then usually you can check your math by checking the units if you want. Frequency, I know I should be solving for hertz. Does the math work out? Yeah, it solves for 1 per seconds, which are called hertz. So my setup is right. I can check the setup just like before when we did statements of equality and converted between units. We did the units just to see if we solve for the right units. And if we solve for the right units, then we said, okay, I know the math is right. Let me actually do the math. Let me plug this in the calculator and see what it gives me. Back in 8th grade when we did scientific notation, I had to do it on a slide rule. Anybody here ever even held a slide rule? Okay. was new to me too. Kind of weird. But that just gives you a touchstone. You know, that was right after the dinosaurs roamed the earth. Man had just gone to the moon and stuff like that. No, kidding. I was actually born after Kennedy was shot, so I'm recent. Any questions that you have for me on this problem? Again, this is completely walked through on page 103 in your book. But I just wanted to walk through with you because, yeah, you could have looked at it and read it. And if you applied yourself, I think you probably could have figured it out. But now you've got another example of us doing the work together and walking through that problem. Now that we have solved for frequency, and the problems you're going to have that use formulas as well as this one for energy, joules is equal to Hertz, and then Planck's constant, you may get a problem that gives you energy, or excuse me, solves for energy by giving you Planck's constant and frequency, or they may give you wavelength. If they give you wavelength, that means you have two-step problem. If you're given wavelength, you've got to convert wavelength into frequency, which you can do using this process right here. And then the second step is to use the frequency to solve for energy. Don't take a shortcut and be wrong and use wavelength here to solve for energy. This formula is based on frequency. Even though they're related and they're inversely proportional, okay? You have to use the right variable. You cannot use wavelength in that formula. It has to be frequency. But if you have wavelength, you can convert it to frequency using this. Before we do an energy problem, I want to touch on some of the responses that you put on the quiz with regard to frequency and wavelength. I'm going to try to remember the problem exactly, but here's the general idea. Some of you were talking about speeding up light and slowing down light and, you know, what it means when, I'm thinking of the question that talks about blueness and talks about amplitude. I just want to remind you that you're not altering the speed of light. And some of you kept referring back to slowing down light and speeding up light. It's not slowing and speeding light. It's increasing or decreasing the frequency of the wave of light. The speed of light is how quickly it moves in a forward direction, not how quickly it moves up and down in its frequency, or how high or low it moves in its crest or trough in the wave pattern. Always. Always. It's a constant. It's a physical constant. C does not ever change. Again, for the purposes of our class, this is not theoretical physics. This is chemistry. Okay? The people that deal with changing C, geeks, man. We don't even talk to those guys. Well, we do talk to those guys, but I mean, it's outside the realm where we're dealing with right now. Someday, if they make a discovery on how there's a variation here, it'll impact us. But for right now, it's kind of like using the Bohr model. It may not be perfectly technically correct in all cases, but for our purposes, this is constant. This is not philosophical or theoretical physics. So we're going to treat speed of light as always 3.0 times 10 to the 8th meters per second. So how quickly that wave is moving, and we use the analogy sometimes when we teach it about using a rope. You know, William brought up last night about a hose and water. Ever do that when you're filling a pool or something and you start doing the waves of water as they go in, okay? And if you take the hose and you make this big, long, like, snapping motion, you'll see this big water loop that kind of like travels across. Or maybe if you have a rope or a hose that's hooked to the house, and you don't do that, right? Because it'll pull the bib out and make it leak and all that bad stuff, so don't do this. But if you were to take a rope or hose and kind of snap it like this, and you see the waveform moving down the hose, okay? What we're saying is the speed that the forward edge of that wave moves is like the speed of light, and it goes the same speed all the time. However, the speed at which I move my hand is the frequency. And if you can visualize this waveform, as I'm moving my hand like this, I get this nice steady wave moving down the hose. If I decide to speed it up, and I go faster, and if I consider that the front edge of that wave doesn't go faster than the slow one, it travels at the same speed, I'll have more oscillations. As I speed up how quickly I move that hose up and down, the crests become closer and closer, okay? So think of it this way. As you increase the frequency, you decrease the wavelength. As I then slow down, I slow down the frequency, I lower the frequency, but I increase the wavelength. I make the wave longer when the frequency is lower or slower. And I make the wavelength shorter when I make the frequency higher. That's exactly what's happening with light. Okay? So when the question says, if we make it bluer versus making it redder, if you remember in the Roy G. Biv, the abbreviation for Roy G. Biv, you've got red on one side, right? This represents the spectrum. Roy, nah, that's not gonna work. Roy G. Biv. From violet to red, red is what kind of wavelength? Long or short? It's long relative to the blue side, which is relatively short. And that is how we relate the wavelength. So the big, slow wave moving on the hose, that's going to be reddish. And then as I speed up my hand, the frequency gets higher, but the wavelength gets shorter. It's more blue. So if I put this in terms of frequency, the violet is higher and the red is lower. It's a lower frequency, longer wavelength. A higher frequency has a shorter wavelength. So, if we're thinking about the wave that's formed, as I make the wavelength longer, I'm moving redder. As I make the frequency lower, because I'm making a long wavelength, I'm moving redder. When I take the wavelength and I make it shorter, I'm making it bluer. And when I make the wavelength shorter, the other way to say that is I make the frequency higher. Shorter wavelength equals higher frequency equals bluer light. A longer wavelength, which equals a lower frequency, is a redder light. And so the way I asked you to remember this is if I had a dial that I could turn, and I had a single light in front of me, and as I turned this dial, whether I was changing the frequency or changing the wavelength, they're both related, right? So as I turn that dial, I would be making the light, let's say if I turned the dial and I made the light redder, as I made the light redder, two right responses would be, Mr. Baker, you just made the wavelength longer, or another way to say that is you also made the frequency lower. But if I make the wavelength shorter, that also means that I've simultaneously made the frequency higher and the light would appear to shift to the blue region. So the light would become bluer instead of redder. Okay? Bluer and redder are not the same thing as energy. I don't want you to think in terms of energy here. Okay? Now, it is related to energy on the next step because if you increase the frequency, if you have a higher frequency, yes, you do have higher energy. But we're looking for answers based on wavelength and frequency when you ask that color about the bluer or redder of the wave. Okay? Now, the other part of that is the brightness. And these are both important, okay? So we've just reviewed redder or bluer, what that means in terms of wavelength and frequency, but also brightness. If I had another dial and I turn that dial, it would be exactly like a dimmer in your home. If I turn the dial one way, the light becomes brighter. It doesn't change color. It becomes brighter. And then as I turn it the other direction, the light becomes dimmer. Color doesn't change, which means my frequency and my wavelength, they stay the same. But I can get it brighter or dimmer by changing the amplitude of the wave. The amplitude. That's how far above and below center line it moves. Okay? So the amplitude affects the brightness. The wavelength frequency relationship affects the color. Two different things. On page 108, they do a two-part energy. I think if you have a one-part energy equation, it's kind of straightforward and simple. We'll go ahead and look at a two-part. Everybody that's going to write this down, have it down? Okay, here we go. Let's try to do the two-part energy. Tomorrow, we will go through and do practice problems that by then, if you're going to turn them in, they should be in. And we'll go the ones that are most problematic in there, on those. Looking at the wavelength, the energy question on 108, it says, a light wave has a wavelength of 1.21, has a wavelength of 1.21 times 10 to the negative 12th meters. What is its energy? So light has a wavelength of 1.21 times 10 to the negative 12th meters. What is its energy? Like I said before, we have to go, we can't use wavelength in the formula. It would be a different constant than Planck's constant. It would be written in a different way. But so the way that we're given Planck's constant here, Planck's constant is in terms of joules per hertz. And since it's in joules per hertz, it means we have to have hertz in our equation, so we have to have frequency. Do they? It's one of the examples in the book. 108. Counter fist pump. I got to take that one back. I don't know why the fist pumping, but it's kind of like the little pinky touch you guys had. That's cute. You reached across and did the pinky touch with him earlier. I was like, what's that all about? I missed that one. I'm not editing that. Okay, so solving for energy. Again, it's simple because you don't have a bazillion formulas. You've only got two formulas really you're working with. Energy equals HF and C equals lambda F. So we're going to be solving for energy, which means we're going to use this formula right here, and we don't even have to rearrange it. So energy equals H times F. I wrote it this way, this time with the multiplication sign in the middle. This is correct, as is that. Those are three different ways to look at it. They all say the same thing, that energy is equal to H, which is Planck's constant, times frequency. So E equals HF. Now I need frequency, but I don't have frequency. I have wavelength. Okay. So I have a second formula, C equals lambda F. And I'm looking for frequency. I could rearrange this formula right now, just like we did before, and say, well, I can rearrange this. It's going to take me to that frequency equals C over lambda. It's another way of rearranging that formula to solve for frequency. Now I could, at this point, go through and solve for frequency, and that's what the book does. The book goes through and solves for frequency, and you come up with, according to the book, 2.5 times 10 to the 20th hertz. That is if that's what you need to do to keep this straight in your mind, do that. Just plug in 3.0 times 10 to the 8th and divide it by 1.21 times 10 to the negative 12th, and you will get 2.5 times 10 to the 20th, the frequency. But because I have rearranged now for frequency in terms of C and lambda, I can take this and plug it back into this formula too. Okay, this equals now H C over lambda, right? I just plug whatever I've solved for frequency, I can plug it back into here in this form. So you solve for frequency and plug it in, or you can replace it in the formula and solve it this way. So you make it a one-step problem rather than a two-step problem. If you're really struggling with the concept here, I recommend you do it this way. Solve, plug in the numbers, 3.0 times 10 to the 8th meters per second divided by 1.21 times 10 to the negative 12th meters. Solve for frequency, which again the book gives us here 2.5 times 10 to the 20th. I could go back in then here, use Planck's constant, 6.63, times 10 to the negative 34th, and multiply that by 2.5 times 10 to the 20th. And that would give me the right answer. If I decided I wanted to be trickier and use replacement here, E equals HF, but that is also equal to C over lambda, I could put 6.63 times 10 to the negative 34th times 3.0 times 10 to the 8th divided by 1.21 times 10 to the negative 12th. So one method would be solve for frequency, plug frequency in here, and solve for energy. The other way is kind of like a consolidated method. This is probably the first way I'd recommend you do it. Solve for F and then plug F into that formula. The second way to do it is if you understand the concept, you can be free to do it the second way, which would be substitute for C over lambda for F in this frequency and just do it as a one-step problem. Okay. The one-step problem is probably for those folks who understand both the math of algebra to rearrange the formula and the concept. If you're struggling with the concept or the rearrangement of the formula, use this one to solve for frequency, plug it into this one to solve for energy. The answer here is going to be in joules. 1.7 times 10 to the negative 17th joules. Nope, excuse me, 13th. Let's see, ballpark-wise, another, just a technique again. 6.63 is about 6.5. Okay, 6.5 times 2.5. Well, 2 times 6.5 is 13, right? And then the other 3 is about 19. Now, so estimate this to be about 19 times 10 to the negative 34th times 20th. In the scientific notation with the exponents, when we multiply them together, what do we functionally do? We add them together, right? So this is going to be times 10 to the negative 34th plus 20, which is going to be about equal to 19 times 10 to the negative 14th. Put in appropriate scientific notation, that's approximately 1.9 times 10 to the negative 13th. And see, 1.7 is our actual answer, 1.9 is our estimated answer. So yeah, it's right.
Where'd you get 6.6?
Planck's constant, it's given to you. It's always 6.63 times 10 to the negative 34th. That's the, I didn't write down the units, but it's joules per hertz. And yeah, the way we get this is it's the energy here, the units are joules per hertz, times the frequency here is in hertz over 1. We do the math, you're left with joules.
So that's always H, 6.63?
Always. And it's always given to you. You don't need to memorize it. So it'll be given to you. You just have to use it. Okay, so mathematics-wise, on the quiz, these were the two where, you know, she's absent, but she missed how to do this, and so was saying, can we please go over this on Monday? We did. Unfortunately, she's absent today and didn't get to do the review. But for those of you that struggled through these problems, did going over these example problems again, is it helpful? Hopefully you understood it. Okay? So again, Monday after school is my normal tutoring time. I'm going to stay again tomorrow afterwards for help people for a while if you need more help before Wednesday. Wednesday is the module exam. Wednesday is the last day of classes for the grading period. Homework was due today. If you didn't turn it in today, turn it in tomorrow. There's homework for tomorrow, which is the EPPs. And then on Wednesday, bring in your review questions. I've already got yours, okay? But if you haven't turned in the review questions, bring those in. Submit them with your exam, and I will consider those for extra credit on the exam. Does anybody know who is the owner of textbook number 10? Okay. Does everybody have their textbooks? because this was left in the hall last Friday. So, do you have yours? Do you have yours now?
So because I thought it was that, I just brought it real quick. So
Okay, I can check if you're not sure.
you want me to go check my locker real quick, make sure I don't have it?
Actually, I want to find out whose book it is anyway. So, how much time do we have? Just a few minutes, right? This is your opportunity then. I'll check it after class. If it's yours, I'll bring it to you.
Okay, be able to use your notes during that test?
I haven't decided yet. And I usually won't tell you because I truly do want to motivate you to be prepared. And then still, if I allow you to, see that as a benefit. Don't expect to be able to use them, but be prepared that if I say you can use them, you've got something you can actually use. For me to tell you, you're not going to get to use your notes. Some of you will not take notes. It'll actually hurt you. The uncaring me would be like, hey, suffer, big deal. That's why I put the 2 tombstones on the board at the end, because some of you are going to take the exam and go home and I'm dead. But hopefully in preparing, do the work, do the problems, put them in your notebook, work through them, show you're working through them. And that part of it too is if you do problems and you for homework and you do the problems, you get them wrong and you figure out how to do them, go back and if you see in your notes that you took notes wrong or something, correct your notes. Make sure what you have is actually going to help you on the exam. It'd be terrible to go back and use your notes and your notes be wrong. Okay? Or maybe as I've explained something today, the frequency wavelength relationship and the amplitude relationship to the brightness and to the color. If your notes don't have that clear, go back and supplement your own notes. Fix them. Writing it down 4 times is not necessarily beneficial as it is having it 1 or 2 times and having it right both times. So going and looking at your notes saying, is that what I actually wrote the way he described it today? No. You know what? I make mistakes. I may have in this presentation accidentally in my mind inverted something. I would hope that somebody would go, but that's not what you said last time. Call me on it. I'm not up here to try to trick you. I'm up here to try to help us all come to a better understanding of the material. So if I make a mistake, sometimes I'm listening to the tape and going, wait a minute, what did I just say? And rewind it and go, okay, I was right. I just maybe said it in an awkward way. So I try to work on my own presentation as well. And even if you don't improve me enough right now to help you, help me be better for the next class that I teach. Now you're touching his knee? Really? I'm not editing that out either. You guys are, like I said last time, you guys don't. All right, I'm going to check the owner of the book. You're dismissed at the bell.